it's a time. It's some time for me now that I haven't given an online talk, but we are used to this format since the pandemic, and it's really very good that you keep up that format, that you continue this form of communication. So I'm very happy to talk today in this seminar. Um, as you can see, I gonna talk about homological algebra and persistent theory, and I sort of outlined that I will not use. Sorry, I outlined that I will not require prior knowledge of topological data analysis. So the first. Let me first introduce a little bit what's the plan of the talk. So what you can see here is kind of the um, what you can see here is what they call the pipeline of persistent series. So you would start with some finite data set and associate to it a module, a representation of some poset, and then we like to study this module by just looking at some vector that we attach to the module. So I'm trying to explain that to some extent. First, I will start talking about the general setup, what is a representation of a poset. And then I talk about this story. We start with a finite data set and attach a module to it. And then I spend most of the time on the last part studying certain invariants which are associated to this module. And please feel free at any time, if you have some questions, please feel free to raise your hand, to write a message in the chat, or any other way you wish to communicate. So let's start. As for the context, I consider a poset partially ordered set P. Most of the time, my posets will be finite because I come from finite dimensional algebras. And we consider representations over a field K. I was traditionally considering algebraically closed fields. However, you can allow any field in that context. And in topological data analysis, they like to study representations over the field with two elements because then you can easily implement it on a computer. So let's do that. Uh, any poset over any field. So we study the category of representations of that poset P, and the category of representations in persistent theory is defined as the category of functors M from P into the category of finite dimensional vector spaces over K. They really prefer that functorial point of view. So functor meaning we want to view our poset P as a category. So the poset P is a category whose objects are the points, and we just have one morphism from X to Y whenever X is smaller or equal to Y in the poset. So you can view a poset as a category, and then a representation is a representation of that category. We represent every point in the poset P by a vector space, and morphisms are represented as linear maps. In this sense, it really looks like representations of quivers. However, I mean, I do not know what is your preferred background. So instead of this representations as functors, you could also study modules of the incidence algebra of the poset. The incidence algebra being the algebra, normal incidence algebra of the poset. So the algebra whose basis, if you wish, is given by basis elements which are indexed over the ordered pairs, and multiplication of these basis elements follows transitivity. So you could study modules of the incidence algebra you could study representations of the poset, and these two categories are equivalent, whatever you are more comfortable with. Yeah. I don't really know my audience. Can I make a quick vote? So if you prefer the left-hand side representations of poset as functors, can you quickly raise your hand or show me on Zoom, like this is what you like? Good, thank you very much. So a couple of people prefer this one. If you're more at home at the ring series side and you love modules, can you show me your hand who is more on the module side? So I think there's a majority for modules. Thank you very much. Uh, but as I said, these two are two equivalent points of view of the same thing, the category of representations. And we do know that, say, if instead of posets we study quivers, so we have rep Q, and rep Q is equivalent to the path algebra of the quiver. So this is the same equivalence. Yeah. So you can view representations of quivers as a representation, or you can view modules. You can study modules over the quiver, over the path algebra of the quiver. So this is the same story. These are equivalent categories. And really, really in TDA, in topological data analysis, really they take this functorial point of view. So that's our situation. Now, let me explain you a little bit the story of persistence homology. So persistence homology is part of what is called TDA, topological data analysis. In TDA, you start with a data set, you compute the homology group of the data set to obtain a modular persistence module, and then you use this module to study topological features of the data. So let's start here. We are given a finite data set, call it D. And my data set are those points here that, as you can see in this simple example, vaguely form a circle, right? And we kind of, I mean, we see it's a circle, but we kind of want to train a computer to recognize that as a circle. Yeah, because imagine in general, this is D is not 2, but D is some high-dimensional space, and there's a million of data points, and you don't see anything. We really want to train the computer to recognize topological shapes. And how is this done? Um, so the the topology, let me go back. The topology of that space isn't very interesting. These are discrete points. Yeah, so this is discrete topology. You don't recognize anything interesting there. So in order to see that these point cloud forms something like a circle, what people in TDA do is they blow up each point by a certain radius, epsilon, and then they take the union of the balls around each point of radius epsilon, and they consider then d epsilon, which is this the union over all those balls, and then you see it somehow starts to connect. It sort of forms something that, as a topological space, is homeomorphic to a circle. So if you blow up the radius of your points, you see that actually we have a circle. And the radius here, epsilon, this is a variable. Yeah, I mean, we allow ourselves to increase the radius. And when epsilon, the radius epsilon is smaller than epsilon prime, then we have a union of larger balls. So this d epsilon will be contained in d epsilon prime. This means we really get a system of topological spaces depending on the parameter epsilon. So we have uh, an R filtered system of topological spaces. Yeah. And to each member, to each member of that system, so to each topological space d epsilon, we compute now the piece homology group of index p. In TDA, usually they consider only H0, so they count connected components in order to recognize clustering in the data, or they would measure H1 to recognize non-contractible circles, and sometimes H2. It's really H0, H1, and H2 that is considered in TDA. But listen, to every epsilon, to every value epsilon here, we get one vector space, the homology group of that topological space, the epsilon. And it is a filtered system. So for every epsilon, we get one such vector space. And when there's an ordered pair, epsilon, epsilon prime, homology is a functor. So it induces a linear map between the homology groups between those vector spaces. And homology is not an exact functor, so even if this was an inclusion, this linear map need not be injective. So we just get uh, such a system of vector spaces together with linear maps between them whenever epsilon is small equal epsilon prime. So we really have something that, in the notion we discussed before, is a representation of the real numbers when we view it as a partially ordered set as a poset. So in that sense, this functorial point of view comes very natural. And I wanted to give you a little example on GeoGebra to see how this works. Okay, this is not GeoGebra. Let me go here. Yes. So in you see my GeoGebra picture. So we have a set of data points, A, B, C, D, and so on, just a very few set of points. And there's a slider where I can increase a radius. You see what's going on? So I increase a radius, a ball around each point of a certain radius. And when the radius is large enough, those balls start to connect. And the app here gives you the complex of the connections, the nerve of this topological space. And when we increase it large enough, then suddenly we find something that looks like, as a topological space, like a circle, okay? And then we can continue increasing the radius until everything fills up and we don't see anything anymore. So that's why we want to keep the parameter epsilon variable, because a priori we don't know which radius is the good one where we see topological features. So we really want to consider this as a representation of the whole real numbers. Okay. Are there any questions so far? No, doesn't seem to be the case. So some remarks. Um, some remarks. First, D, we start with a finite set of data D. So there's the homology groups will almost always be the same when we increase a continuous parameter epsilon. So there will be finitely many values of radii epsilon 1 to epsilon n where the homology actually changes. And we can focus on just those finitely many values. So if I do this, then I can replace that poset representation M by a representation of that quiver of type AN, which is linearly ordered. I just consider the values at these finitely many values, epsilon 1, epsilon 2, up to epsilon n. So I come back to early classic quiver representations. This is a representation of a quiver of type AN. Next remark is that what I showed here, this was just one construction. To be completely clear, this is called the Czech complex. And we have other constructions in particular, so that one construction gave us what is called a one parameter persistence module because we vary the radius one parameter. But in general, there's more advanced versions where you have bifiltrations of topological spaces. So you would have two parameters, say the radius and the density parameter or something. So your poset would really be in this case, a two-dimensional grid. Like we study representations of that poset, and this is then called two-parameter persistence theory. And there's also more general posets that could occur. Okay. Mm, Finally, in one parameter persistence theory, as I said, we can view those persistence modules really as representations of a quiver of type AN, and we do know the representation theory of the quiver of type AN. Yeah, AN is a representation finite quiver. Every module, every representations decomposes into a direct sum of indecomposable representations, and the indecomposable representations over the quiver Q of type AN are given by what they call intervals. So every indecomposable, representation theory of AN, every indecomposable is of this form. We start at some index A. Um, we start at some index A with a vector space with a one-dimensional space K. Then we go up to some index B, staying one-dimensional and identity maps, and outside are zero maps. So this is an indecomposable. Every indecomposable is of this form, and any given module M is isomorphic to a direct sum of such indecomposables. In topological data analysis, they described in the module M just by the collection, by its indecomposable summons, so by a collection of intervals. And they like to draw those intervals in what they call a barcode. So say there's an interval from A to B, and there's another interval, another interval. So there's a bunch of intervals which corresponds to the direct sum decomposition. They draw those intervals in a shape that resembles a bit the barcode, and they say this is the description of the module. Yeah, and the idea is that the longer intervals correspond to persistent features, to something that is topologically interesting, and shorter intervals are some features that are not really relevant. So the word persistent theory comes from the fact that they are looking for topological features that persist through a longer time frame or through a larger range of radii epsilon. So if we go back to this GeoGebra example, let's do this again. So we start with a discrete data set and we increase the radius until they start to connect. So topology changes here, yeah. So this was our first epsilon, something changes. And then starting from here, we see the circle, yeah. So starting from a radius, if I read this 3.4, our homology group H1 will be non-trivial. And then we go up, we have this hole in the middle until the hole disappears at a radius of 6.7. Okay, so back to our example, we would see something from A equals 3.4 to B equals 6.7. So this is one long bar where H1 persists. So that seems to be something relevant to the data. However, if I change my picture here a little bit and say I have some noisy point in the middle, what you can see is that there's some H0 appears at several short places and it disappears immediately. Yeah, there's some holes in the data that appear for some short time and they disappear very quickly. So in general, you would expect some shorter intervals appearing quickly that are just coming from some noise in the data, and they are kind of, we want to ignore those. So we are interested in kind of long intervals in that persistence diagram. So this is the story for one parameter persistence theory. If we have more parameters in the two parameter case, say, then the poset is, as an algebra, the incidence algebra of the poset is a wild algebra. So one parameter persistence is representation finite. We just can store the information the module decomposes in all its indecomposables, and they are given by a nice description. In the wild case, we don't have any nice description of the indecomposables. We don't really know what are the indecomposable modules. We could still decompose it, but we have no nice description available of all the indecomposables, no visualization. So there's nothing available like this barcode. And we have to find other ways to associate to the given module M some meaningful information that we can store in a vector, and then hopefully give this vector to a computer and let the computer study different data sets. Yeah. So that's the challenge here, that in this case where we have wild posets, wild representation theory, we still want to find some meaningful information that we can extract from a given module. And in order to do so, we study, so now I start with my third part. We study what is called additive invariance. Yeah, so we are given a module. I view this module M as a member uh, of the split Grothendieck group of representations, and to M here, I want to associate phi of M some vector of finite size. So the split Grothendieck group here is just the free abelian group with basis the indecomposables, meaning an additive map phi here would be just, I give myself for every indecomposable member in this abelian group Z to the I, and then I extend it linearly to direct sums. Yeah, so really, I want to attach some value to every indecomposable module. And examples of that are, for instance, the rank invariant. This is something that has been studied a lot in persistence theory. So the rank invariant, given any module M, would associate to this the collection of ranks of all the linear maps between every comparable pair of indices. So whenever I have I smaller equals j, I get a linear map from mi to mj. I compute the rank of this linear map, and then I store the information of all those ranks in a vector. This is one invariant that you can associate to a given module for any poset. And I mean, if I smaller equal j, this includes the case I equals j. So when I is equal j, the map, the structure map of the module is necessarily identity, because we consider functors and categories, and this is the identity map. And the rank of the identity is nothing but the dimension of the vector space at this point. Yeah. So this rank invariant contains, in particular, as information, all the dimensions, all the pointwise dimensions. So calculating the rank vector, we compute in particular as a subvector the dimension vector of the module, the classical dimension vector of the module. So maybe I should have started with this. One way to attach a vector to a module is the dimension vector. And the dimension vector per se is not interesting in TDA, because the dimension vector doesn't see if some information is transported throughout the poset. I mean, it only measures the pointwise dimensions. It does not see the rank of the linear maps going from one point to the other. So I do not see if any topological information persists for a longer time. Yeah. Therefore, the dimension vector isn't too interesting for topological data analysis. Just as a little verification, let's consider an example. I have a module which is a representation of a quiver of type A3. So it's given by vector spaces k squared, k, and these two linear maps here. So the dimension vector would be 1, 2, 1, because we store the pointwise dimension of the vectors, of the vector spaces. And if I compare to the rank invariant, so the rank invariant has the dimension of 1 and the dimension at 2 and the dimension at 3. So this is the part that we have seen before already uh, in the dimension vector. So 1, 2, 1 enters here, 1, 2, 1. But the rank invariant stores more information, like the rank of the map from 1 to 2. This is a map of rank 1 here. The map from 2 to 3 is a map of rank 1 itself. And if you compose the two maps, so if I go from 1 to 3, so from k to k, I compose these two matrices, and if you do the matrix multiplication, you see they compose to the 0 map, so the rank here would be 0. So this rank information stores a good amount of information. We see if any, say, if any features, if any topological information survives from here all the way to there, and the answer is no, it doesn't. So that's a very meaningful invariant. It's well studied in persistence theory. Okay, so let's move on from here. What we want to do now, we have these two invariants, the dimension vector and the rank invariant, which are classically studied in persistence theory. And we want to generalize these two invariants, um, enlarge them, add more information to learn more about the given module. Yeah. So one way to do that, I start with the dimension vector. Yeah. One way to do that using homological information is, as you know, the pointwise dimension, the dimension at vertex I of a module M can be described as the dimension of the space of homomorphisms from the indecomposable projective Pi into M. Yeah. So M at I is isomorphic to Hom Pi to M. So instead of storing the dimension vector, I could store the vector of dimensions of the homomorphism spaces from the indecomposable projectives to my given module M. And you can see that here we test our module by harming into M from a given set of modules, here the indecomposable projectives. But you could easily generalize this by adding more test modules. So instead of the projectives, you give yourself your favorite set of modules, the injectives, or any other module that you wish to test your given module M with. You just measure the dimension of the homomorphism space from your given set of modules into M, then you get more information about M. So in that sense, it's easy to generalize the dimension vector to get more information. We just harm M with a larger set of indecomposable modules. So that's one way to use homomorphisms to generalize the dimension vector. And another way would be using real homological algebra. So if you do homological algebra, you would consider, say, I give you a module M and you want to do homological algebra, you would tell me, well, let's compute a projective resolution. I would say a minimal projective resolution of the module, right? So I give myself an exact sequence with projectives going into M. And the information then we can extract from M. Remember, we want, at the end of the day, we are looking for a vector that we can associate with our module M. So the vector M that is stored in that projective resolution would be the entry associated to M in the Grothendieck group uh, of representations. So we take the alternating sum of those entries of the projectives that appear in the projective presentation of M. That's the uh, element of the module M in the Grothendieck group. Yeah. And these two informations are really equivalent. Yeah. I mean, the dimension vector and the element of M in the Grothendieck group are really equivalent information. There's a base change. I mean, on the left-hand side, we take as a basis the indecomposable projective. On the right-hand side, we take as a basis of Zm the simple modules, and there's a base change that transforms left-hand side into right-hand side. So that having the dimension vector is equivalent to computing the entry of M in the Grothendieck group. So this also could be generalized using relative homological algebra. So instead of projective resolutions, you can give yourself a larger set of modules by which you want to compute um, resolutions. So we give ourselves a larger set, and instead of projective resolution, we compute approximations given by a larger set of modules. And then we iterate these approximations and we compute the same thing, the alternating sum of everybody that appears here along the way. So that also gives us a way to extract more information. And to some degree, as these two are equivalent, these two methods, 1 and 2, are equivalent, you can compute those relative, these resolutions, or you can compute dimension of Hom spaces. In the back of the story is tilting theory, which tells us these two sets of informations are equivalent. So I will focus for now on the simpler version, dimension of homomorphism spaces. Okay? And then let's do that. So the one theorem that I would like to discuss is a theorem from 2021 by Botnan, Oppermann, and Udo. And they showed that computing the rank invariant over any poset, computing the rank invariant of a given module M is equivalent to computing the following set of dimensions of homomorphism spaces. So first, we need to compute the dimension of the homomorphism space from all the indecomposable projectives. This corresponds to the fact, as we have seen before, the rank invariant contains the dimension vector, and computing dimension vector is really equivalent to this. And then the rank invariant is a finer invariant. It carries more information, so we need to compute dimension of Hom space with some other modules, some non-projective modules. And those non-projective modules, Botnan, Oppermann, Udo found out are the modules which they call the hook modules, HAB. So whenever we have a pair of indices A smaller b, we define the hook module HAB as the quotient of PA by PB, the indecomposable projective associated to A divided by the one at B. So if I illustrate this in the two-dimensional in the two-parameter case. So imagine our poset is such a two-dimensional grid. Then the indecomposable projective would be the module which starts here in A and then extends in dimension 1. So there's a copy of K at all the vertices that follow A. So in this whole region here, we are one dimensional. Yeah. And now for this hook module, so you start with the projective in A, so it would be this whole region. But then you divide by the projective in B, yeah, the quotient by the projective in B. So what you are left with is that shaded region here that kind of has the shape of a hook. So that's why they call them the hook modules. Okay, good. So this is the theorem. Computing the rank invariant is really equivalent to computing dimension of Form spaces from this given set, the projectives and the hook modules, into my given module M. And they prove this theorem, and just by, to some degree, elementary calculations, they do some base change. They show really computing one invariant is equivalent to computing the other invariant. However, they don't really explain you why or where do these hook modules come from. They just show this works. Yeah, this is equivalent information. But we don't really understand why did those hook modules appear. And this is the question that I would like to discuss now. So I really would like to address the question, why is the rank invariant related to those hooks, to those hook modules? So that's what I want to answer. But we are trained mathematicians. We are trained to respond to certain keywords, like there's a theorem here. So I want to give you a proof of that theorem. Yeah. Now, but really the point that interests me, how can we see those hook modules appearing in the proof? So let's look for an explanation why those modules appear and not somebody else. Yeah. Okay, so let's do this. The rank invariant. To compute the rank invariant, we need to compute the rank of the linear map given a module M over the poset, and we take two points A smaller equal B. There's a linear map from MA to MB, and we want to compute the rank of this linear map. This is what we have to do. So if we look at the two-dimensional grid example, we look at a module that is indexed over such a grid here, and in this grid there's a point A, there's a point B, and we look at poset representations. So all those paths here commute, and there's really one linear map from MA to MB, and this is the linear map whose rank we are interested to compute. So given our module a representation of the poset, so there's vector spaces everywhere, we focus just on the vector space here and there and the linear map between them. This is all we are interested in. So in terms of representation theory, we can view it in the following way. Say we take this quiver, this one arrow from A to B, and we embed it into the poset. So our quiver here is embedded into this larger two-dimensional grid. We embed it just A goes to A, B goes to B. We really have an embedding of a sub-poset, an embedding of a quiver into my larger poset algebra. And given the module M over the large poset P, we can restrict it to the smaller sub-poset. We restrict M to that quiver. And the representation theory of this quiver Q is well known. The module restricted to Q is a module over the quiver algebra A2. So in A, this is the Ausländerreiten quiver of representations. There are two simples in A and in B, and there's the large projective module, which is two-dimensional k, k, and 1. So if I take my module M and I restrict it to Q, it will decompose into a direct sum of these three indecomposables. It will decompose in a certain number of copies of the two simples in A and B and the projective. That's what we know. So we are interested, remember, we are interested to compute the rank of this module, yeah? So the rank of this linear map. So the rank of this linear map, if I go into this interpretation, I restrict M to the quiver Q. Here it decomposes as a sum of these three indecomposables. The two simples do not contribute anything to the rank. Yeah, I mean, the symbols are given by the maps of the symbols are zero maps. So the only summand that contributes to the rank of this map is the projective. And for every occurrence of the projective, the rank increases by 1. So really the rank of this map is the multiplicity, is the number of times how often does the projective PA occur as a summand when I restrict M to the quiver Q. So in my direct sum decomposition here, this is really the multiplicity Y. So the multiplicity of PA in M restricted to Q is the rank of this linear map. Let's start like this, that's okay. And then I want to interpret the rank in terms of some dimensions of Helm spaces. Yeah, so I do know the Ausländerreiten quiver. I know that PA maps into itself. I do know PA maps into the simple in A. So I can control all the Helm spaces. So the multiplicity, how often does the indecomposable projective PA appear in the restriction of M? I can measure this as the dimension of the home space from PA to M. But PA maps to itself and to the symbol. So just this one, I make a mistake. So I need to subtract the dimension. How often does the symbol map into M? If I take this difference of dimensions of home spaces, I get exactly the multiplicity of PA as a summand of M restricted to Q. So that's very good. We replace computing the rank invariant by computing a certain difference of dimensions of home spaces from some modules PA and SA. This is exactly what we were looking for. We were looking to interpret the rank invariant. We wanted to interpret the rank invariant as computing dimensions of certain homomorphism spaces. However, we compute them over the original poset P, and we are not supposed to compute those dimensions over some smaller quiver Q that we embedded. Yeah. So now we have to do the lifting. We have to transfer those results, dimension of Helm spaces, over that sub-quiver Q into the larger poset P. Okay. So fortunately for this, we have a general theory available. So say in my poset P, in the poset algebra, in the incidence algebra, Kp, I look at the idempotent, which is given by the sum of the two idempotents at the two vertices A and B, and then I multiply my poset algebra with that idempotent on the left and on the right. I get back my poset algebra for this quiver Q, the one arrow, and associated with such an idempotent is there is a bunch of functors, so I can go from the larger poset representations to the smaller poset representation by restriction functor. But restriction functor is an exact functor. It has functors in the reverse direction. So there is one functor that goes back. So there's one functor that goes back from representations over Q into modules over Q KP. And this is the adjoint functor of restriction is called induction. And induction is given by tensor product. I tensor over Q with this module PE. So that's the functor that goes from here to there. And this is a well-developed theory. This is an adjoint pair of functors. So as an adjoint pair of functors, it allows me to transport information about homomorphism spaces on this side into homomorphism spaces on that side using the well-known adjunction formula. Yeah, so if there are any, are there graduate students here? I would like to test you. I would like to ask you, can you give me the adjunction formula in that case? So I'm given a module U and I'm given a module M on this side. How can I compare the homomorphism dimension into M with homomorphism side information on the other side? I don't see you giving me any answers. So I hope you do know that if I compute M restricted to Q on the right-hand side, this is equivalent, this is isomorphic as computing homomorphism space of the induced module U on the other side. So this is classical adjunction formula. Yeah, so this and this in U, this would be PE tensor U. Okay, so using my adjunction formula, I can transport information that I know about Helm spaces on Q to Helm spaces over the larger poset. I can lift this information. So this is what we're gonna do now. So remember we had our rank invariance was this dimension of homomorphism spaces over Q, yeah, hom from the projective into the restriction and hom from the symbol in A to the uh, restriction. And using adjunction formula, I can transfer this into dimensions of hom spaces over the poset P. And I use now my adjunction formula. So the induction is the left adjoint of restriction. So it is a right exact functor. It maps projective to projectives. So the projective here goes into the projective there. Yeah, I mean, these are the indecomposable projectives. Here's the projective over the smaller quiver Q. Here's the projective over the larger poset P. But projective go to projective. So I do know that here I do have PA. And I need to compute the value there, okay? So to compute the value there, I give myself a projective resolution of the simple module SA. The simple module SA, as we have seen, has a projective cover PA, and the kernel will be the projective PB. Good. So now I take this projective resolution. I do know induction is a right exact functor. So when I want to compute the tensor product, I'm not very good in computing tensor product. I just use the fact that induction is a right exact functor. So I replace this value here by the co-kernel of what I get here. So if I compute that, the projective here goes to the projective. So this is the projective in P. That's the projective in P. And I can compute the value of the induction functor here, since I have a right exact functor, as the co-kernel of this map. So I do get PA quotient by PB. Everything computed over the poset P. So what we do obtain here really is this PA over PB. I do get at this point, really. PA over PB, I do get the hook module, which appeared in the proof of Botnan, Oppermann, Udo. So really what it tells us is when I know the dimension of the Hom space in P from the projectives and from the hook modules, then I compute this difference and then I compute the rank for every pair of indices A and B. Conversely, if you know all those ranks, then you also know the rank MAA, but the rank of MAA is just the pointwise dimension, and the pointwise dimension is the dimension of Hom from the projective. So if I know this rank and this dimension, then I can also compute that dimension. So these two pieces of information are really equivalent. Knowing all the ranks or knowing all those dimensions is equivalent information. I can compute one from the other. I can go from left to right and vice versa. So this really proves the theorem by Botnan, Oppermann, Udo, and I think it explains in terms of representation theory why do we get these hook modules. And I'm at the end of my time. I just want to tell you that based on this proof of the theorem, we can now think about other embeddings. I mean, what did we embed so far? We embedded the quiver with two vertices, but instead of that, we can embed any representation finite quiver. So we can consider embeddings of posets where S is hopefully representation finite. We control its representation theory. And then with any of such embedding, we are given a beautiful situation, recollement um, of functors. There's restriction. It has two adjoints, left and the right adjoint. And then we can generalize every representation U, every indecomposable here that we know. We can lift it to representations using induction here. And then we can consider a generalized set of modules, generalized hook modules, and study those. So for instance, when S would be such a poset, type A3 quiver representation, you get more interesting modules. Yeah, I mean, there's a large indecomposable. This large indecomposable has a projective resolution given by two projective, and we quotient by a third one. So we would have like one large projective direct sum another projective, so they add up to something two-dimensional here, and then we quotient out a third projective, so the modules are getting more interesting. So we would study dimension of homomorphism space into our given module M by modules that have such a structure. Yeah, so there's many ways to extend this theory into more interesting invariants. And um, and this is everything I wanted to tell you. Thank you very much.
So thank you, Thomas, for your very nice talk. Are there any questions or comments?
So may I ask one question?
Yes,
Yeah, sure.
please, John.
Yes. In the general embedding, yeah, exactly this slide. Does it make sense that one thinks about one point extension just, and then as a kind of induction, then one can get this general situation?
Yeah, you can. One point extension is a good technique, of course. I mean, remember the situation we are interested in is where P is the poset P is like a two-dimensional grid, like something of this form, right?
Yes.
And you can do 1-point extensions. Say, how do you extend? Say you extend at this point, so you would consider something like S would be this subposet. You see what I'm doing?
Yes, yes.
The problem with this is that P is too complicated. It is wild. And the
Yeah.
S here is still too complicated because it's also wild. So you need to do a lot of 1-point extension until you get to smaller cases. And really the strategy here is we want our S to be a representation finite poset.
Oh, yeah.
When we restrict M to that smaller part, then we control the representation theory. We know all indecomposables. If we restrict it to some smaller poset, which is still wild, then kind of, then I still don't know what to do. Yeah.
Yes, yes, yes. Exactly.
Yeah.
Oh, thank you.
So, are there any questions or comments? And I have two questions. What about the dimension 3?
In dimension 3, so when it's not not a two-dimensional grid, but kind of like R cube, like a three-dimensional grid. Yeah. I mean, yes, there are filtrations of those topological spaces that have been studied. The poset obviously becomes even more complicated. I mean, in dimension 3, I would really suggest to study embeddings of a D4 type subquiver. Yeah, I mean, in dimension 3, we can embed this quiver in. I mean, imagine you have like a grid that is very complicated, but we can study embeddings of D4 type subquivers. And that has not been done in persistent theory, but I personally think when you look, I mean, this is a representation finite quiver. We know it's indecomposables, and I think that would be very relevant information. The indecomposables that look like this. There's a large indecomposable. So does this large indecomposable appear in a given module when we restrict it to D4, yes or no? I think this would be some relevant information. Thinking about representation theory. Yeah.
Thank you. And what about the other invariance which is importance in the persistence theory? I mean, you speak about two of them, dimension vector and rank function. Is there any, for example, is G vectors also its importance in some sense, or?
Yeah, they do consider G vectors. I mean, when we they actually do not consider G vectors, but this is a good point. I would like to encourage them to consider G vectors. I mean, we give ourselves a projective resolution of the module. Like so, and or maybe it's not a projective resolution. Maybe it's a resolution by other objects. But what they consider is really the alternating sum of all of those. Yeah, and the G vector would be kind of just the class of P0 minus the class of P1, right? And maybe we focus just on this bit information and not on the whole vector, because in general, I mean, they have a problem because this resolution this can be very long, and they want to give it to a computer, and we don't. It's hard to find bounds on the length of the resolution. So why not stick to just to the first two entries and consider the G vector? I think this is a very good idea, and we need to convince them that this is a good idea.
Well, thank you very much. Are there any questions or comments? So let's thanks Thomas again. Thank you very much.
Thank you.